In the last video, we covered dense neural networks at a high level and continued to show how this high-level understanding relates to large language models. In this video, I provide a concrete example of a dense neural network used to recognize handwritten digits. The base code for this example comes from the TensorFlow.org website. I added additional code to show more details of what is happening. At a high level, the neural network looks like this. The input layer consists of 784 neurons that are every pixel values from a 28 by 28 image. It feeds a hidden layer of 128 neurons. The output of the hidden layer passes through a dropout layer that resets 20% of the values to 0. The result is then passed to the output layer that calculates the probability of each digit between 0 and 9. In terms of weights, or parameters, the network has a little over 101,000 parameters. With this in mind, let's get into a Jupyter notebook running in Visual Studio Code. The notebook is available on GitHub. You can find the details in the description. This notebook uses TensorFlow to represent the weights and the Keras APIs to put together neural networks. Keras contains numerous implementations of commonly used neural networks building blocks, allowing for fast experimentation. The notebook also uses the popular Python libraries Matplotlib, NumPy, and Pandas. The first thing we do is load the training and testing dataset used in this notebook. This is a well-known dataset that provides 70,000 28 by 28 grayscale images of handwritten digits. The original grayscale values are integers with values between 0 and 255. Instead of using the original values, the model we create takes in real values between 0 and 1 by dividing the original values by 255. This helps the model to converge faster to a solution with less potential issues. We already saw the high-level diagram of this model, so we can move to the code that creates it. The code is pretty simple. We create a sequential container that includes the multiple layers. The only addition to the diagram is the flattened layer that takes a 28 by 28 image and flattens it to one dimension of 784 values. Note also that the dropout layer is set to 0.2, meaning that 20% of the values will be randomly selected and reset to 0. Finally, the model is compiled and optimized for accuracy. The loss function returns the probability of each of the 10 possible answers. Before we get to training the neural network, let's look at what a 28 by 28 matrix looks like. Remember that the number shown represent grayscale values. We can also display an image using Matplotlib. This gives a better idea of what is being processed. It is possible to access information of a compiled model. Attributes can be accessed directly, and utility functions are also available, such as the summary function. As we can see, we get the layer we expected. You may have noticed a difference in the number of parameters compared to what was shown in the diagram. In the first dense layer, we saw 100,352 parameters, and the summary returns 100,480, a difference of 128, which is the number of neurons in the dense layer. This is to take into account a bias value that is always included in the linear equation used in a neuron. Similarly, the summary function returns 10 more values than what was calculated to account for the bias values in the neurons of this layer. Let's look at some of the weights. When we get the weights, we get a list of arrays where each element represents a layer. Let's look at the output of a cell execution. We see that the array shapes match the number of neurons we have in each layer. The first array is 784 by 128 for a total of 100,352 values. The first column represents the weight of each input value going into the first neuron. We can see the first 20 of those values with both positive and negative values. The second array represents the weights the first pixel receives from the first 20 neurons. We can see that the first value of each array is the same since it is the weight of the first pixel going to the first neuron. The other values are different. Now we can train the model. It goes through all the training data 5 times in random groups of 32. Now that the model is trained, we can evaluate its accuracy. We see a model with a 97% accuracy. Let's use the model to predict the values of all the digits images from the test value dataset. Looking at the first prediction, we see 10 floating point numbers. Each number represents a probability of each output neuron that stands for the possible answer between 0 and 9. We can see that the value at position 7, when counting from 0, is much larger than the others with a value very close to 1. Let's reformat the output with a 4 decimal digit precision so it is easier to read. As we can see, the result is 0.9999 at position 7. Let's print the first 10 predictions. We find that the first value was indeed 7. We also see that the model is able to predict the values very accurately. In this video, we see that we can use a library like Keras to create a dense neural network with high-level operators and train its weights through forward and back propagation to achieve an optimized neural network with high accuracy. The goal of this example was only to demonstrate concretely what it means to create and train a dense neural network. You should not take this neural network as a proper solution to this problem. Still, it should solidify your understanding of dense neural networks presented in the previous video, Neural Network Introduction. Please comment on this video, and I'll see you next time on Bite-Sized Data Science.